Welcome back to this video series on the Comptia Security Plus course, encryption and hashing concepts. It can help to pose the following question: what is it that we need to encrypt? Without a doubt, it is the data that needs to be encrypted, but more specifically three types of data: data in use, data at rest, and data in transit. Data in use can be described as actively used data undergoing constant change. For example, it could be stored in databases or spreadsheets. Data at rest is inactive data that is archived, backed up to tape or otherwise. Data in transit, also known as data in motion, is data that crosses the network or data that currently resides in computer memory. Cryptography concepts. Cryptography is the practice of hiding the meaning of a message. The word is roughly derived from a Greek word cryptos, meaning hidden, or graphene, meaning to write. However, in cryptography, it is not the message that is hidden, but rather the significance of the message. Let me give a basic example of cryptography. When I was younger, some people would keep a black book of names, phone numbers, and so on. You probably wouldn't use a black book today, but I digress. Anyway, a couple of these people did something that fascinated me. They would modify phone numbers according to a code they had developed. This was done to hide the true phone number of a special friend from their parents or from teachers and so on. It's a basic form of encryption, although at the time I didn't realize. I just referred to it as code. Essentially, it worked like this. The person with the black book would take a real phone number such as 5550386. They would then modify the number by stepping each number backward or forward X number of steps. Let's say the person decided to step each number between 0 and 9 backward by 3 steps. The resulting coded phone number would be 2227053. I'm sure you see how that was done, but let's break it down so we can make an analogy to today's data encryption. Table 14.1 shows the entire code used. Original number 012345678 minus 3789012346. In this example, each number between 0 and 9 corresponds to number 3 digits behind it. By the way, the numbers cycle through. For example, the number 0 goes 3 steps back, starting at 0 to 98, then 7 in a around the bend fashion. This is an example of cryptographic substitution. Let's analyze each of the components in the table. Can be likened to today's computer-based encryption concepts. The original number is like the original file data. The modifier is like to an encryption key. The modified number is like to encrypted file data. I call this the black book example, but I would guess that others have used similar analogies. Of course, this is a basic example. However, it should serve to help you to associate actual computer-based encryption techniques with more tangible data. Now, for other people to figure out the original phone numbers in the black book, they would have to do the following. Step 1, gain access to the black book. This is just like gaining access to data, depending on how well the black book is secured. This by itself could be difficult. Step 2, break the code. This would be known as decrypting the data. Of course, if the owner of the black book was silly enough to put the phone number encryption table in the book, well, then game over. It would be easy to decode, but if the owner was smart enough to memorize the code and tell it to no one, making it a secret code, it would be much more difficult for another person to crack. Plus, the person could make the code more advanced. For example, table 14.2, original number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, minus 9, minus 8, minus 7, minus 6, minus 5, minus 4, minus 3, minus 2, minus 1, minus 0, 1, 3, 5, 7, 9, 1b, 3b, 5b, 7b, 9b. In this example, there is a different modifier or key for each original number because the modified numbers have duplicates. We place a letter next to each of the various duplicates to differentiate. This is tougher to decrypt due to the increased level of variations, but on the flip side, it is that much harder to memorize. Like computers have a harder time processing more advanced encryption codes, and hackers or crackers have a difficult time processing their decryption. At this point, only one person has legitimate access to the encryption codes. However, what if the person wanted to share phone numbers with another person but still keep the numbers a secret from everyone else? This would be known as a secret key. We refer to this basic concept as we go through this chapter and next. Now that we have been given a basic example, let's define some terminology in a more technical way. We start with cryptography, encryption, ciphers and keys. You might want to read through this list twice because each definition builds on the last. Cryptography. By definition, cryptography is the practice and study of hiding information, or more accurately, hiding the meaning of the information. It is used in e-commerce and with passwords. Most commonly, encryption is used to hide a message's meaning and make it secret. Encryption is a process of changing information using an algorithm or cipher into another form that is unreadable by others unless they possess the key to the data. Encryption is used to secure communications and to protect data as it is transferred from one place to another. The reverse decryption can be accomplished in two ways. First, by using the proper key to unlock the data, and second, by cracking the original key. Encryption enforces confidentiality of data. Cipher. A cipher is an algorithm that can perform encryption and decryption. A basic example would be to take the plain text word code and encrypt it into ciphertext using a specific algorithm. The end result could be anything depending on the algorithm used. But for example, let's say the end result was ciphertext zlab. I don't know about you, but zlab looks like gibberish to me, although if you Google it, I'm sure you'll find all kinds of endless fun. You've probably already guessed it. At my cipher, each letter of the plain text word code was stepped back 3 letters in the alphabet. Historical ciphers used substitution methods such as this and transposition methods as well. However, actual algorithms today are much more complex. Algorithms are well-defined instructions that describe computations from their initial state to their final state. If-then statements are examples of computer algorithms. The entire set of instructions is the cipher. Key. The key is the essential piece of information that determines the output of a cipher. It is indispensable. Without it, there would be no result to the cipher computation. In the previous bullet, key, that was the act of stepping back 3 letters. In the first black book example, the key was stepping back 3 numbers, a modifier of -3. Just like a person can't unlock a lock without a proper key, a computer can't decrypt information without the proper key using normal methods. The only way to provide security is if the key is kept secret, or in this case there are multiple keys. If one of them is kept secret, the terms key and cipher are sometimes used interchangeably, but you should remember that the key is the vital portion of the cipher that determines the output. The length of the key determines its strength. Shorter, weaker keys are desirable to attackers attempting to access encrypted data. When two users exchange encrypted messages, it starts with the key exchange. The method of this exchange will vary depending on the style of cryptographic algorithm. Keys can be private or public. A private key is known to a specific user or users who keep the key a secret. A public key is known to all parties involved in encrypted transactions within a given group. An example of a private key would be the usage of an encrypted smart card for authentication. Smart cards, express card, PC card technology, and USB flash drives are examples of devices that can store keys. When private keys are stored on these types of flash devices and delivered outside of a network, it is known as out-of-band key exchange. An example of a public key will be when two people want to communicate securely with each other over the internet. They would require a public key that each of them knows. When this key transfer happens over the network, it is known as an in-band key exchange. Encryption types such as AES and RSA are types of cipher key algorithms, or simply as algorithms. We refer to them as algorithms during the rest of this chapter and the next. There are basically two classifications of key algorithms: symmetric and asymmetric. Symmetric versus asymmetric key algorithms. Some cryptographic systems use symmetric keys only. Others use symmetric keys only, and some use both symmetric and asymmetric. It's important to know the difference between the two and how they both can be used together. Symmetric key algorithms. The symmetric key algorithm is a class of cipher that uses a single key, identical keys, or closely related keys for both encryption and decryption. The term symmetric key is also referred to as the following: secret key, private key, single key, and shared key. Examples of symmetric key algorithms include DES, 3DES, RC, and AES, all of which we discuss later in this chapter. Another example of a technology that uses symmetric keys is Kerberos. By default, Kerberos makes use of a third party known as a Key Distribution Center, KDC, for the secure transmission of symmetric keys, also referred to as tickets. The private key is common in the workplace. Let's say a user encrypts a file with a private key. Generally, that same key or very similar private key is needed to decrypt the data. Imagine that the user left the organization and the user's account, and therefore the user's key was deleted. How would you get the data back? Well, if the system has a recovery agent, you could use it to decrypt the file, otherwise the data will not be recoverable. It's important to understand that private keys and by extension symmetric key systems must be approached carefully or data could become lost. Following are two types of symmetric key algorithms. A stream cipher is a type of algorithm that encrypts each binary digit in the data stream one bit at a time. A block cipher is a type of algorithm that encrypts a group of bits collectively as individual units known as blocks. For example, the Advanced Encryption Standard AES algorithm can use 128-bit or 256-bit block ciphers. Block ciphers can work in different modes, including electronic codebook (ECB), code cipher blockchaining (CBC), cipher feedback (CFB), output feedback (OFB), gallows counter mode (GCM), and counter CTR. The modes define how a message is divided into blocks and encrypted. For example, ECB divides a message into blocks of plain text, and each block is encrypted separately. CBC is commonly used mode that builds on ECB or XOR ring, each block of plain text with the previous cipher text block that was created. CBC is one of the modes that require a unique binary sequence and initialization vector or IV. For each encryption operation, the IV can be vulnerable, as in the CBC IV attack, where the predictable IV can lead to the deciphering of all blocks. Because each one is based on the block previous, secure coding concepts should be employed when using CBC, or a separate block mode should be selected altogether, such as GCM, which is considered to be more efficient mode. The mode chosen will depend on the purpose of the encryption and the application it is being developed for. Symmetric key algorithms require a secure initial exchange of one or more secret keys to both the sender and receiver. In our black book example, we mentioned that people might possibly want to share the cipher with someone else. To do so, they would need to make sure that they were alone and that no one was eavesdropping. It is also so with computers. The secure initial exchange with secret keys can be difficult depending on the circumstances. It is also possible to encrypt the initial exchange of the secret keys. Symmetric encryption is the preferred option when encrypting and sending large amounts of data. This is in part because it usually takes far less time to encrypt and decrypt data than asymmetric encryption does. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.